All right, everybody, let's finish up. We are going to talk about Taylor series, okay? And so the idea here is we've already talked about how to take a function and turn it into a power series, but what about those coefficients, right? What about the AN terms, the coefficients of our variable terms, right? How do we get our hands on those? And we're going to discover that in the Taylor series. So here we go. Okay, so let's keep talking about our Taylor series here and maybe start by just asking, what is a Taylor series? Well, let's develop this for a second. Suppose that, oh, I don't want red, I want blue. So let f of x be represented by a power series. At x equals c, with an interval of convergence c minus r, c plus r. Okay. So we have f of x equals 0 to infinity an x minus c to the n, which is a0 plus a1 x minus c plus a2 x minus c squared, and so on. Now, f prime of x is going to be a1 plus 2a2 x minus c plus 3a3 x minus c squared, and so on. F double prime of x will be 2a2 plus 2 times 3a3 x minus c plus 3 times 4a4 x minus c squared. And I'll do one more here. And really, hopefully, you're starting to see a pattern. Sorry, it's 2 times 3. So f triple prime of x is 2 times 3, a3, plus 2 times 3 times 4, a4, x minus c. Oh, come back. Plus 3 times 4 times 5, a5, x minus c squared, and so on. And so what we can notice here is that kth power, kth derivative, is k factorial ak plus 2 times 3 all the way up to k plus 1, a k plus 1, x minus c, and so on. Well, let's let x equal c. And when we do that, watch what happens. We're going to get f of c equals a0, f prime of c equals a1, f double prime of c equals 2a2, f triple prime of c equals 2 times 3 a3. And the kth derivative at c equals k factorial ak, which gives me a formula for that kth coefficient. Okay. And what that lets me do is that lets me write my function as, I'm going to use T for Taylor series, as a Taylor series. We'll have f of c plus f prime of c, x minus c, plus f double prime of c over 2, x minus c squared, plus f triple prime of c over 3 factorial, x minus c cubed, and so on, okay? And so the advantage now is that we know how to get those coefficients. And so if f has a power series representation about a, sorry, it should be about c, which is given by the usual, then the coefficients are given by this formula. How powerful is that? Okay, so let's put this into some practice. The Taylor series of the function of f at c is given by this sum. And notice that in this sum, there's my ANs that you're used to seeing. Now, if we take that Taylor series and build it about 0, then it's known as a Maclaurin series. Okay, so Maclaurin series gets its own attention, but it's really just a Taylor series at about 0, all right? Okay, here's some examples. So we have a continuously differentiable function. We want to find the 5th degree polynomial, T5, about c equals pi thirds for the function, and here it is, f of x equals sine squared x. Okay. So I know I need some derivatives, right? So let's start with that. Right, f of pi thirds. Well, sine of pi thirds is what? Root 3 over 2. So we have 3/4. F, well, let's take some derivatives here. So f prime of x is going to be 2 sine x cosine x. F double prime of x is going to be 2 cosine squared x minus sine squared x, which is actually just 2 cosine 2x. Third derivative is going to be negative 4 sine 2x. And the fourth derivative is going to be what? Negative 8 cosine 2x. And then my fifth derivative is going to be 16 sine 2x. Okay. So now I can find my coefficients. A0 is 3/4. A1 is f prime of pi thirds, which is going to be, well, sine of pi thirds is root 3 over 2 times 1/2. That's root 3 over 4. So what do we have? Root 3 over 2? And then we have 2 f double prime of pi thirds all over 2, which is what? Cosine 2x. So it's 2 pi thirds. Cosine of 2 pi thirds is negative 1/2 times 2 is negative 1, so negative 1/2. And then a3. If I just keep going here, let's see, negative. So we have third derivative of pi thirds over 3 factorial. So what's my third derivative there? Let's see, sine of 2 pi thirds is going to be root 3 over 2. So we have negative 4 root 3 over 2 all over 6, which is, let's see, that looks like negative root 3 over 3. A4, it's going to be negative 8 cosine 2 pi thirds over 4 factorial, which is 1/6. And you can go off to the side and work these through if you need to. And then 16 sine 2 pi thirds over 5 factorial, and that's going to be root 3 over 15. Okay, so I've got all my coefficients now, so I can write my polynomial. And the way we note it is t subscript 5 for 5th degree. And so 3/4 plus root 3 over 2 x minus pi thirds minus 1/2 x minus pi thirds squared minus root 3 over 3 x minus pi thirds cubed plus 1/6 x minus pi thirds to the 4th plus root 3 over 15 x minus pi thirds to the 5th. Okay, there is my 5th degree Taylor polynomial. All right. So how about a Maclaurin series for cosine x? All right. So let's think about this. So f of x is cosine x. F prime of x is negative sine x. F double prime of x is going to be negative cosine x. F triple prime of x is going to be sine x, and so on, okay? So remember, Maclaurin series means our C is 0. So A0 is going to be cosine 0, which is 1. A1 will be negative sine 0, which is 0. A2 is negative cosine 0 over 2, which is negative 1/2. And I'm looking for a pattern here, okay? A3 is going to be sine 0 over 3 factorial, which is 0. A4 is going to be cosine 0 over 4 factorial, which is 1 over 4 factorial. And so what I want you to notice is that it's really only the even terms that have any values here, and the signs are alternating, right? And so let's see, cosine x 0 to infinity. I need the signs to alternate. And then it's my even terms that show up. So x to the 2n over 2n factorial, okay? Again, 1, which is 1 over 1 factorial. Negative 1/2, that's negative 1 over 2 factorial. A4, that's 1 over 4 factorial, and so on, okay? And so there's my Taylor series, my Maclaurin series to be more specific. Okay, and finally, let's evaluate this integral. And we're going to use that Maclaurin series, okay? So I'm gonna say recall that cosine x, you know, I'm gonna do this. I'm gonna say cosine u negative 1 to the n, u to the 2n over 2n factorial, okay? So here's what I'm gonna do. X squared cosine x squared. X squared is gonna operate as that u. So I can write this as follows. Okay. Oh, sorry, x squared to the 2n. And so what I have, and what's remarkable here is, maybe I probably should have started with this, but if you were to just try to integrate this, good luck. You got x squared, and inside you have an x squared. You're not going to use a chain rule. You're not going to use integration by parts. But here, and we're about to do, taking advantage of the series expansion, it's actually pretty doable. So let's just keep going. And what I'm going to do next is I'm going to absorb that x squared into my sum, okay? All right, so let's integrate both sides, okay? X squared cosine x squared dx equals, well, let's integrate this other side. And, you know, I'm summing these ends here. So what I can do is this. And now I apply that integral formula from the last theorem of that section a couple back. Well, just a power rule, right? X to the 4n plus 2 plus 1, so 4n plus 3, all over 4n plus 3, okay? All right. So there we have the Taylor series and the Maclaurin series. So go ahead and again, spend some time digesting these. There's a process you want to get used to. And in terms of just problems, right, there's on the one hand, we want to be able to write Taylor polynomials, find those coefficients, and list out, you know, to whatever degree term is prescribed. And on the other hand, we want to use these expansions to differentiate, or in the last example, integrate and it can actually make things pretty simple. So I know it's new. I know it's a new way of thinking, but I want you to be familiar with what the Taylor series is, and always keeping in the back of your mind, though, where the thing converges, okay? Because that issue of convergence doesn't go anywhere. Once we have this Taylor series, what x's is it good for? I don't want to go expanding some function if about some point, if it's outside where the thing converges, right? So we have a point that we build our Taylor series about, but we want to make sure that the domain that we're using for our x's falls inside that radius of convergence. Okay. All right. I will sign off here and wish you the very best in your studies, and lest I forget, happiest of studies.